Oh yeah, good. Oh god.
Yes, take your attendance.
No further.
Okay, class, so let's we start. Okay, so we are almost like 60% of the quantum. Another 2 parts to go. The finish of this topic. Okay. So this is the 12th topic. So we have 15. We have 3 to go. So we have about 4 weeks. As I said, we'll be finishing about 1 week before your trial. Okay. So, so at the background, I believe that you are doing your passes like sets. Okay, like now you can cover like 2/3 of the passes. Okay. Okay, so we done up to second one. So the most demanding need lots of explanations. The part the one we did for 3 lessons. So we learn about photon, a new concept. What is photon? 2 marks. What is photon? A packet of energy of an EM radiation dependent to frequency. Okay. And second, photoelectric emission. What is photoelectric emission? 2 marks. The release of electron from a metal surface when EM radiation is exposed to the metal. Don't say light, say EM radiation. Okay? Gamma, everything is included. What is the three outcome against the wave theory? Three outcome which against the wave idea of the light. First, the emission is instantaneous, right? The emission is instantaneous. One outcome which against the wave idea. Waves thought what? Wave predicted what? Wave predicted that should have a delay. Okay. Second, very important 3 outcomes. There are 4. 3 outcomes. First is instantaneous. Second, anybody? Another outcome which is against the wave idea, which happens in the photoelectric effect. Second is the existence of what? Existence of threshold frequency. The existence of threshold frequency. Wave predicted what? Any frequency should release the electron. Just matter of time. Okay. Energy is nothing to do with frequency according to wave. Okay. But here they found that there is existence of threshold frequency. There is a certain minimum frequency. You need to go more than a certain minimum frequency to emit the electron. Okay. So the second outcome against the wave idea.
What happens if the electron gets 2 photons?
Yeah. So according to his Einstein's theory, he said one electron only able to get 1 photon. No 2 photons. His theory predicted only 1 photon. If it's 2 photons, then nothing goes all wrong. Okay. So according to, because he wrote in a theory which he don't have proof, So he thought this how it should look like according to his imagination. Then later, finally, only after 16 years it was proven. So according to him, only 1 photon. Okay. Good to think about that. Okay. More research needed. Okay. But it's proven so far, no problem. So second, existence of threshold frequency. Third evidence. Man, this past year they will ask these 3 evidence. Always. What are the 3 evidence against the wave idea in photoelectric effect? Emission is instantaneous. Second, existence of threshold frequency. Third, the kinetic energy is independent of the kinetic energy of the electron is independent of what? Intensity. The kinetic energy of the electron is found to be independent of intensity. Wave predicted intensity possesses the energy, determines the energy. So more intensity means more kinetic energy of the electron. But they found that kinetic energy of the electron which comes out nothing to do with intensity. Okay. So 3 evidence, 3 outcomes. Okay, then we talk about of course HR. Then we talk about how Einstein explained it. Okay, so HR equals to work function EK max. Okay, so then work function can be transformed to what? Work function can be written as what? HF naught, right? Work function is HF naught. What is F naught? What is F naught? Threshold frequency. Okay. Kinetic energy can be transformed to what? A millican help Einstein. So what is the formula you replace? Kinetic energy is E times stopping potential. Okay. So a millican very expert in electric field. So you say the kinetic energy of the electron can be obtained by using electric field, stopping potential. Okay. Then leads to the proving. Okay. So the proving of this this formula, this outcome, this outcome is proven. So this graph will be also very important. The graph you're going to ask. So this graph you have to predict what is gradient, what is the y-intercept by using the Einstein's formula. HF equals to work function plus dk. The axis is most of the time they'll change frequency versus stopping potential, frequency versus kinetic energy. Sometimes frequency versus wavelength also goes. Okay, wavelength. Wavelength means the photon formula is what? Photon energy HF, right? HF they transform to wavelength. So HF we can write in terms of wavelength how? Hc over lambda, right? So they plot 1 over lambda versus frequency. Also got. So the axis they will change. So use your linear law to predict what is the gradient, what is your y-intercept. Okay. Common one, stopping potential and kinetic energy. Okay. Okay. So now let's continue today's lesson. Okay. Yeah. So this is what we did. Okay, we're going to continue. Okay. We'll do this. Okay, now after this, what do you call unusual type, the photoelectric experiments are very unusual in science, which really what do you call threaten the science world because of the idea of light is a wave. Now threatens the idea. Okay, so now we'll come to in a big confusion. Is it light? Light we thought is a wave. Okay. But now it looks like light shows particulate nature, okay, in a packet. So what is going on? So why suddenly the light shows a particulate nature? Okay, what is the proof? So your seniors I asked this question after I teach this. I asked them. So what is learned from photoelectric effect? So one student said light is not a wave. Totally wrong. Okay, so light is a wave. It's proven, but light now shows dual character. There is another character it shows when to react with the matter. Okay, so light is actually wave. What is the proof light is a wave? Can diffract, refract, interfere. So it has proven light is a wave, but when it interact with matter, when it comes to energy transformation, it shows the particle character. Okay, an usual particle character has been shown. So light 99.9% is a wave, but sometimes it shows the particle nature, okay, when you interact with matter. Okay, but still confused. So how can these two character in the wave? Then later, another scientist close up this idea. He said de Broglie. Okay, heard of de Broglie? Okay, one of the scientists he got a prize with his master's thesis. Master's faculty. This master's thesis idea was so excellent, explaining this idea called wave particle duality. Okay, so he said, okay, light is a wave, exhibit particulate nature, but he said particle also exhibit wave nature. See, particle also shows wave nature. What is the proof? Electron diffraction pattern, we call it. Electron, that's the next slide. For just time being, I go to the next slide. Electron diffraction pattern is a proof that particle shows wave nature. Electron is particle or wave? Electron is a particle. Okay? But electron shows diffraction pattern. It diffract. And electron from this is a carbon film. Okay. Well, the carbon film is actually the slit, the gap between one carbon atom to another carbon atom. The gap is actually same as the wavelength of electron. Okay. You might weird. I say wavelength of electron. Okay. So when the electron passes through this gap, the small slit like one slit, what happens? The electron shows fringes. It's diffracted. Diffracted means the electron only hit at a specific point. Okay? If it's a particle, all must Let's you are all particles. Let's say this is the door, one single slit. Okay, everyone like running out of this door. Say, so you'll be like, let's say, on a trolley or what? Let's say, okay, exceed this one slit, consider like one slit property. You'll be in the same spot, right? All of you. So see, you get one spot. So electron also should be like that. It passes the small gap. You have to hit the same spot. You just only see like a laser beam, just one point. The electron is hitting. But here it shows a fringe diffraction pattern. That means the electron has been spread and hit at a specific point. So electron, which is a particle, shows a wave property. It shows wave phenomenon, diffraction. Okay. So de Broglie said wave as a particular nature, photoelectric effect proves that, but particle as a wave nature, electron diffraction is the proof. Okay. So de Broglie comes out with another very controversial equation. Okay, go back to this slide. So you give a very controversial equation. De Broglie, this is the equation he proposed by de Broglie. Lambda equals to h over p. Okay. Why is it very controversial? Lambda is the wavelength, h is Planck constant, p is momentum. Okay. P stands for momentum. Why is it controversial? For the first time in an equation, on the left is wave property, on the right is the particle property has been connected in one formula. Okay. Who possess momentum? Particle. Who possess wavelength? Wave. But this formula does that a certain wave can have this much of momentum. Okay. A certain particle which possesses this much of momentum can have it has a wavelength. Do you have momentum? Yeah. Are you a particle? Particle or wave? About the particle, right? One single unit. You have momentum, right? In our question in exam, they will ask Usain Bolt when he runs, what is the wavelength of Usain Bolt? It sounds weird, yeah? So they will ask that. What is the wavelength possessed by Usain Bolt? The wavelength, they won't tell just wavelength, they will tell de Broglie's wavelength. They call it de Broglie's wavelength. Okay? So h over p, h divided by the momentum you possess, you divide, you get the wavelength value. The wavelength you possess by h. Okay? So that means according to de Broglie, you are a particle, but you have wave property within you. You can diffract. According to this idea, you can diffract. That means all of you type your, let's say, type your eyes, or another, let's say, tennis ball. A tennis ball. Okay, there is a small ball. If I hit 1,000 tennis ball, passes the small ball, and there is a wall. Okay, when the tennis ball passes the small ball like a single slit. Okay, the tennis ball must go and hit only at a specific point. So the diffraction pattern, according to this idea. Okay, but come on, tell me. Planck constant, you know the value, right? Come on, calculate. Let's say Usain Bolt 80 kilogram. Let's say 70 kilogram. 70 kilogram Usain Bolt runs with a 10 meter per second. Okay, calculate its momentum. Can you calculate for me what is the wavelength possessed by the Usain Bolt? The de Broglie wave. Come on, somebody. Take the mass of the Usain Bolt 70 kilogram. What is the Planck constant? Yeah, use the Planck constant, 6.63 times 10.34. Mass of the Usain Bolt, 70 kilogram, speed 10 meter per second. How much the wavelength? Everybody? How much? Anyone? 9.46 times 9.46 times 10 to the power of negative 37. Negative 37. Okay? So the wavelength is too small or too huge? Very, very small. If the wavelength is too small, easy to diffract or difficult to diffract? Very difficult to differentiate. You can't see, as a human which possess a very huge momentum, you can't show the wave property because your wavelength is too small, according to me. Okay, so very weird, huh? So electron, proton, all as a particle, as a wave property. Wave also as a particle property. Okay. Okay, so remember this formula, D cognition, lambda equals HOP, P is momentum. Okay. It linked to Einstein's theory of relativity, but we're not going to do this. Just remember this one. Lambda equals HOP. Okay. So, this idea, if electron never diffracted, this idea is into the dustbin. But because he has the proof, electron has been shown diffraction pattern, so his idea was considered. Okay, wave particle duality. Okay. So next time they ask, what is meant by wave particle duality? Wave shows particulate nature, and particle also shows wave nature, the other way around. Okay. What is the proof that wave shows particle nature? What is the proof that wave shows particle nature? Photoelectric effect. Okay. Photoelectric effect, wave shows particulate nature. What experiment particle shows wave nature? Electron diffraction pattern. Yeah, is that electron diffraction pattern. Moving electron displays diffraction pattern exhibit particles exhibit wave properties. Okay. So they use an electron gun to fire the electron to a graphite. Graphite acts like a sweep for the electron. Okay. And why they select graphite is they found that the wavelength possessed by the electron, when do you get the best diffraction? What is the condition to have best diffraction when passed through a slit? The wavelength must be about the same as the gap, right? The A must be about the same as the wavelength. So they found that the wavelength possessed by the electron is exactly about the same as the gap between the graphite atom. Okay. From one atom to another atom, the gap, right? The electron pass through, the gap is equal to about same as the wavelength of the electron. Okay. Wavelength of the electron. So when the electron passes through that graphite gap, it produces the diffraction pattern. Okay. Okay. So now tell me, if electron never exhibit wave property, let's say you don't have wave property, what is the expected outcome in this experiment? Is it going to show fringe? Just one straight line. So we call it as a uniform distribution. Okay, we found a uniform distribution on the fluorescence screen. Like uniform distribution means just one bright spot. Electron cannot show diffraction. Okay, so uniform distribution. Okay. So if it's a particle, if you don't have wave property, it should show a uniform distribution, just one bright spot. Okay. Now more question has been asked. If the speed of electron is increased, what happens to this fringe? More significant diffraction or less significant diffraction? When the speed of the electron, I say decrease, right? Okay. When the speed of the electron decreased, what happens to the diffraction pattern? Become more significant, less significant?
Less significant.
Why?
Momentum
decrease, so lambda will increase, so big wavelength means more significant is the diffraction, less significant? More significant, right? So the diffraction should be more significant. So what happens? More significant means the fringe get further. Okay. So remember, when the speed of the electron decreases, the momentum of the electron decreases. According to lambda equals HOP, wavelength increases. So more significant diffraction will be portrayed of the screen. Okay. Okay. So this is So he got a Nobel Prize for this, all quantum, all of them. But this guy is quite unique because his master's thesis portrayed this, okay, this equation. But later, this is very controversial. The formula, the diffraction is the proof. Okay, maybe I can. Let's see. Where's the video? Oops. Okay, later. Okay, so yeah, so wave particle duality. This is the diffraction pattern. Okay, so now don't get confused when you see a question like this. So weird for yesterday, but today onwards you can ask a question like this. What is the de Broglie wavelength for a 10-gram bullet traveling at a speed of 300 meters per second? So every particle has wavelength, de Broglie wavelength. Okay. So 10-gram bullet. So what do? You find the momentum, H over P, you get the wavelength. Okay. So an electron as the wavelength. But out of the ABC, can you tell me without calculating? Just without calculating, can you tell me which is going to possess the highest wavelength? ABC. Which one do you think will possess the highest wavelength? Smallest momentum, highest wavelength. So which one? ABC. Most probably. I think most probably electron, right? Very little mass. Very little mass. Could be C2. A, B or C. Definitely not bullet. Yeah. So very small wavelength will show the diffraction pattern. Until now, research shows only electron shows diffraction pattern. Not even proton. Okay? Electron the one shows diffraction pattern. Okay? Very tiny little particle which has a very little momentum, has a significant wavelength, prove the idea of de Broglie. Okay? So this is working. So we can skip this. Just find the momentum, H over P, you get your wavelength. Okay? Mass and velocity. Okay? Okay, so that's a small part. So when de Broglie said that, then I think the problem faced in early 19th century about the light is a wave of particle has been solved. So conclusion now is wave as particle nature, particle also as a wave nature, wave particle duality. Okay. So
what's the difference if they both possess a similar property?
Wave is more, light is more to wave. Okay. Electron is more to particle, but sometimes they exhibit the opposite property. Sometimes. Okay, when the particle can exhibit wave property quite clearly, when the momentum is very low. Okay, you possess. You show the suddenly you show the wave property. Okay, you as a human, if you have a very low momentum passing this small this door, okay, goes to your eye. Okay, many of you without using your brain. Go straight. When your momentum is too small, according to him, he predicted that you can hit the wall at a different location, show the fringe pattern. Yes. Not proven. Only for electron. For time basis. Okay. So this idea maybe sounds still not that balanced, but what happened? The idea of de Broglie was used by Niels Bohr. Okay, you know who's Niels Bohr, right? Niels Bohr who did some adjustment to the atomic structure. Okay. So what Niels Bohr does to the atomic structure? What is contribution? Yeah.
Prove that the electron was something.
So electron has a certain specific energy level.
Yeah.
Electron has a certain specific energy level, proven by Niels Bohr. Okay. Who's the first guy said about atomic structure? Dalton. Then Then who's that? Rutherford. Rutherford is the main contribution, nucleus and electrons surrounding it. Then after the Rutherford model, we thought is the best model, but there is a downfall for Rutherford model. Okay, so Rutherford proposes in 1911 alpha scattering experiment. Know these 19 years. So we proved that nucleus is positively charged surrounded by electrons. But his model got one drawback. Okay, the drawback is this. Okay, this idea again newly introduced to you, but according to classical electromagnetic theory, okay, Maxwell, okay, Maxwell, another scientist, okay. So he predicted that, he proved that, and when a charged particle accelerates, when a charged particle accelerates, a new idea, when a charged particle accelerates, electron accelerates, proton accelerates. When they accelerate, they give up. The charged particle accelerate, they continuously emit radiation. They give up EM radiation. Okay. When the electron accelerates, it gives out EM radiation. Okay. So the EM radiation has some energy. So this leads to what? The electron loses energy and slows down. Okay. So another important point, newly introduced to you, any charged particle accelerates, you are EM radiation. Okay, proven by Maxwell. So the electron moving according to Rutherford model, because the electron is going around the nucleus, is it accelerates?
Yeah.
Which direction it accelerates? Towards the center of the nucleus, right? Circular motion. So the electron accelerates. Because the electron accelerates according to EM theory, Maxwell theory originally, the electron should release EM radiation. Okay, then the electron should lose what? Kinetic energy. So what should happen to the electron? Eventually should fall to the nucleus. So electron should fall to the nucleus, the atomic structure should be just destroyed. Okay, it should not have electron. Okay, it should get into the nucleus. But this never happens for the atom. The electron just continuously going around. Okay, so that's the drawback of Rutherford model. Okay, Rutherford model, nucleus is fine, but the electron is got problem. Electron can't have any energy level inside. Okay, so Niels Bohr. So Niels Bohr applies quantum theory. Okay, he used the idea of what? De Broglie, the Wavelet idea. They derived one full page of derivation. He found that the energy levels for electron. Okay, it's one and a half page of derivation. Okay, maybe you can check on the continuous with this. Okay, he got a formula which tells you that electron has a specific energy level. Okay, so you propose electron travels in a stationary orbit. This leads to possible energy levels for electron. So yeah, so electron only can have certain energy levels. Okay, according to Niels Bohr. Okay. So this is the derivation of that ideal. I skip this. This is extra. So this is how he proposes. Okay. This is energy levels of electron for hydrogen. Okay, for hydrogen atom, and N1 is the quantum number. So this is the first energy level electron can occupy. Down here is like the nucleus. Here's the nucleus. Okay. So this is like you can go one round, beat like that. Okay. This is one part of it. Okay. So nucleus is there. So close to nucleus is the first energy level. Close to nucleus. Then second energy level, third energy level. Okay. The energy level gets closer and closer and go further. Okay. This is what he proposed. Okay. And the electron only can stay in this energy level. They only can stay in this energy level. Okay. They can't stay in between. No way. These are the places where they can stay. Okay. Yeah. So electron in each orbit have a definite energy. Okay, that's proposed by Niels Bohr, and they move in that orbit without radiating any energy. Okay. The n could be of an infinite number. N when infinite, it possesses a zero potential energy. like gravity. Okay, your potential energy now is highly negative or positive. You are having highly negative potential energy or positive potential energy, highly due to gravity. What type of potential energy possess? Positive or negative? Negative, right? You have a negative potential energy. Why negative potential energy? Due to attractive force. Any potential due to attractive force is negative. Okay? So same concept for this electron. Electron trapped to the nucleus, so it's attractive force. The electron also same like us. Okay, we are like electron. Like planet of Earth, here is the nucleus. Electron here, we are analog. Okay, so the electron also has a negative potential energy. They have a negative potential energy. You yourself, let's say when you move away, what happened to your potential energy? Become less negative, right? Same thing happens for the light. Negative 13.6 is the lowest potential energy the electron possesses, quite close to nucleus. But when you go further up, high energy levels, the potential energy reduces. Okay, reduces. And infinite potential energy is zero. Exactly same as your gravity. Okay. So the free electron, when the electron reach n infinite, that means we say the electron is free. Okay, free electron. Okay, free from the atom ionized. Okay. So the energy levels are negative, indicating the loss of potential energy as the electron draws nearer to the nucleus. So N1 is the lowest potential energy. It's got special name. It's called ground state. Okay. Ground state is the lowest potential energy, and electron can occupy ground state. Grounded. So N is the quantum numbers from the quantum derivation. Niels Bohr got these energy levels by using the idea of de Broglie. Lambda equals to HOP. Okay. So if de Broglie formula is okay with the diffraction pattern, but his idea was again shows that is correct by the energy levels for electron. Okay. Okay. So Niels Bohr says that electron will stay at a particular energy. Let's say it stays at N1. It's going around N1. Suddenly, what do you call? It's a metal atom. So the electron inside the atom is at the ground state going around. Okay. Suddenly, let's say you heat the metal. Okay. You heat the metal, or you shine light on the metal, photoelectric effect. Okay. So the electron will get the photon, right? It gets the energy. When the electron gets the energy, and the electron, let's say, ground state, the electron is at the ground state, and the electron get energy, what happened? The electron can jump to the high energy level. Jump to the high energy. Okay? So this line tells that what is the possibility the electron can jump? Okay? So from N1 to N2, let's say energy required 2 eV, electron volt. So if the electron get a photon of 2 eV, it absorbs that 2 eV, it jumps to 2. Okay? The same thing, if you got energy enough to jump to N3, it jump to N3. Okay? So the electron is able to jump up, going up, when it receives energy. How it can receive energy? By shining light, by heating, by collision of another electron. Okay? You collide, the electron was collided with another electron. Another incoming electron going to collide. The electron can get energy. 3 ways like this. Due to collision of electron, it can get energy. The electron get energy through heating, through photoelectric. Okay. Now, see, it was in at 13.6. Okay, for it to jump to 3.39, how much of energy it must receive? Of course, these differences, right? These differences, that energy must be kept inside that photon. Okay. Anyone can calculate 13.6 minus 3.39, how much? 13.6 minus 3.39. 13.6 minus 3.39. What's the difference you get?
10.21.
10.21. Okay. If the electron get a photon of, very important, when the electron get a photon of 10.21, you jump to the first level. Okay? If the electron get 10.23, the electron get a photon of 10.23. It will take the photon? It won't take the photon. You only take the photon which is exactly same as the energy to jump. Important, huh? It only takes the energy, the same energy equal to the energy differences. Okay? A slightly greater than that, it won't take. Okay? So to jump from here to here, you need 10.21 EV, but the photon has 10.23 EV. Electron won't take. Okay? You don't absorb that photon. You only take the specific photon. That's the theory considered by Milborg. Okay? Remember, you only take the specific photon which has the same energy differences. Okay? Anything extra or lower, it won't absorb. The electron won't take that photon. So, electron can stay any level is like. Okay? Now currently this table full of electron. The electron has lots of energy levels. Now currently some electron at ground state, some electron receive this light energy goes up. And after it goes up, is it going to stay there? Currently we only receive energy. But after we finish class, we shut down the light. What happened? The electron will go back, go down. Go down, release back that energy. Okay? Excited, de-excited happens. So all the room here full of atoms, full of electrons, and they receive energy, the electron will go to the excited state, go to the higher energy level, absorb energy. Okay? When you shut down, when it's dark, no light from sunlight or anything, they will go down to the ground state, they release radiation. You got energy. So I think this room is like absorbing radiation and giving out radiation from this atom, all atoms. Okay. So it happens continuously. Okay, the idea better. Okay. One proof for this is your watch. Okay. If a fluorescent can what do you call can shining right in the dark. So why the shining happens for fluorescent? Because fluorescent when it's at light, the electron in the fluorescent jump to the high energy level. Okay. And in the dark, when you go to the dark room, the electron come to the ground state. But the fluorescent, the energy differences, the energy level differences is found to be the energy, the specific energy is found to be in a visible light range, green light. Okay. So you illuminate green light. You get a green light. Only fluorescent does that. Illuminate visible. Okay. That means this table actually give up radiation, but this radiation is not in a visible range. That's why you can't see it comes up radiation. Okay. So fluorescent energy levels in a visible light. That's why it give up light. Okay. So one proof for the energy levels. Okay, so remember, electron, no energy, all of them will be at the ground state. But its probability that some will be stay at 1, 2, 3, and so on. But most of them will come to the ground state and the energy is very low. Okay? You put this small atom, a small plate of graphite which is full of atoms into a freezer. I think all of them go to the ground state. Okay? All of them go to the ground state. And they receive energy, they go up, then lose energy, they go down, release photons. Okay? So this is called excitation. Okay? This is de-excitation. In exam, they will ask how many ways excitation can happen. When it's de-excited, how many different type of photon you can emit? Okay? They will ask that. Okay, for that, let me go to the whiteboard. Okay, you see, let's say you have 1, 2, 3, 4 energy levels. You have 4 energy levels. Okay, 4 energy levels. 1, 2, 3, 4. Okay, when the electron go to the excited state, it's went to the top 4. Okay, then all lights are shut down, so you want to go to the ground state. So this energy level is like stairs, like stairs. Okay, like there is the ball is rolling down. Okay, so this is the 4th energy level, 3, 2, 1. So only 4. So the ball can hit at the second one, straight go to the one. Sometimes the ball can hit the third, second one. Maybe the ball straight come to the one. So got lots of possibilities. Okay. So the electron also has that type of possibilities. This electron first can come down to 3, and the differences in energy E4 and E3. The differences in this energy, that means yeah, E4 minus E3, E4 minus E3 minus E4. So it give out photon. Okay, it give out photon. The energy of that photon is equal to the energy difference. Okay, final minus E3 minus E4. Okay, so photon, what's the formula? Photon, what's the formula? Photon energy, what's the formula? HF or HC over lambda. Okay, right? So this energy equal to HC over lambda. We find the wavelength. If the wavelength is under visible range, then you get a visible light. Okay. So if any atom has energy level differences in the visible range, you get visible light. Okay. So this electron, what are the options you can go? 4 to 3 you can drop, 4 to 2 you can drop, 4 to 1. Okay. The electron at 3 can drop to 3 to 2, can drop 3 to 1. Okay. Electron at 2 can drop to 1. So these are the possibilities. How many different type of wavelength they can produce for 4 energy levels? So 1, 2, 3, 4, 5, 6 different wavelengths you can produce. Okay. The electron is excited. If you got 4 energy levels, 6 different types of wavelength of radiation can be emitted by that atom. Yeah. So next time they'll ask you to draw this. Draw the possible transition. Okay. So start with the top 4, 3, 4, 2, 4, 1, and go to the 3. Because sometimes the electron jump to 3 already, then actually another 2 options. 3 to 2, 3 to 1. Okay. The electron is already at 2, can drop to 1. The 6 different times. Okay. So they never stop that too. They ask you to draw the 6 transition for 4 energy level. They can add more energy levels. They can add 5. They ask you to draw. Okay. But so far in the exam came out 3 energy levels. 4 also very rare. Normally 3 energy levels. 4 sometimes. 5 not even once. Okay. Show the transition. Okay. After that, what they ask? They will ask out of these 6 transition, okay, which produces the highest frequency? Which photon possesses the highest frequency? Which photon possesses the highest frequency? Okay, let's say I put here 1, 2, 3, 4, 5, 6. Which photon possesses the highest frequency? Which has the greatest energy differences? The energy level get and go up, get closer. Which has the biggest energy differences? The energy differences is the photon, energy kept inside the photon, right? So 3. 3 has the highest frequency. Okay. 3. Photon 3 has the highest frequency. Okay. Which has the shortest frequency? Of course, 1. 1 has the shortest frequency. Okay. 3 has the highest frequency. Okay. Which has the shortest wavelength? 3 has the shortest wavelength. They do ask that wavelength. So 3 has the shortest wavelength. Okay. 1 has the highest wavelength. Okay. So this is the transition of electron. Okay. Okay, so I go back. Okay. So this one, the line we draw is de-excitation, and de-excitation. called emission spectrum. We call it, it's an emission spectrum, emitting photon. Okay, electron will go down, it emits photon. So we call emission spectrum. Yeah, emission spectrum. On the right is the emission spectrum. The left we call absorption spectrum. Absorption. Absorb photon and go to the higher excited stage. Yeah. So check carefully the exam. They want emission spectrum or absorption spectrum. Yeah. If the electron, they say throw emission spectrum, that means emitting photon. When the electron emits photon and go down or go up, and go to the lower end. So you draw all the arrows downwards, going down. If they say absorption spectrum, the same pattern, just put all the arrows upwards, going up. Okay. Okay, so this again another nice story by Niels Bohr. He wrote the story theoretical, but need to have proof to award him Nobel Prize. So what is the evidence that electron has energy level? To his idea, it has a specific energy level. Okay, the proof is we come to this later. Just the proof is light spectrum. This is the proof for Niels Bohr's idea. Electron has energy level. Okay, we will discuss this next one. So after they got this light spectra, then Niels Bohr, the fourth scientist in quantum physics series, got Nobel Prize for this. Everyone got Nobel Prize for this quantum physics. Okay. So read about light spectra. So tomorrow we continue. Okay, thanks. So this is the last part actually, last part of this topic. Okay.